Before I start, I think as a last speaker, I should ask the I should thank the organizers of this school to thank for providing us a beautiful opportunity to interact, to talk to each other, to learn something from each other. That was, for me, it was a great experience. I hope this is true for everybody. So let's thank the organizers for this job that they have done. Okay. All right. So this is the last lecture, and as promised, it has to do with non-inflationary beginnings of the universe, alternatives to inflation, which is not very popular subject, but it's always good to have alternatives and to understand if you can design something different from the common law on the one hand, and on the other to see if you can think of observable differences between different approaches, different ideas. So I think it's worth talking about this subject. Well, first of all, we do need long evolution, as we discussed in our previous lectures. We do need long evolution before the hot cosmological epoch to generate perturbations of all sizes, which eventually become superhorizon at the hot epoch, and therefore before the hot epoch. So you need long epoch during which your perturbations, your wavelengths, are initially subhorizon, and then they exit the horizon to re-enter later on at the hot stage. So we do need something very long before the hot stage. So if not inflation, what one can think about? Well, one can think about various options. One is that one can think of contracting universe originally, which then by some miracle bounces, so that contraction terminates, and the universe goes to expanding stage. So this is very old idea, of course, that the universe started off some big, slowly contracting, and eventually bouncing. So this is bouncing cosmology, and there are many reincarnations of this idea. I will talk about one of them. The second is relatively new, which goes under the name of Genesis. Very kind of brave people invented this name, one of them sitting here, Trincarini. And the idea here is different. The idea is that the universe starts off empty, flat, Minkowskian essentially, with very little energy density in it, if any, and then energy density slowly builds up, the expansion speeds up, and eventually you become rapidly expanding, and at some point you have to transfer energy which has appeared into heat. In either case, you would like to have hot universe after this unconventional period of expansion. So these are two possibilities which obviously are different from inflation, or you can in principle have, as Enrique Trincarini and colleagues have written recently, you can marry these ideas with inflation, but that I think is kind of possibly. I mean, it's hard to imagine how you can observe that, because inflation tends to wash out all memory about the previous epoch. Anyway, these two possibilities are non-inflationary, obviously, but there are difficulties. So let me tell you what difficulties are and whether one can go around these difficulties. One difficulty is the following. If we write down let's stick to general relativity and write down the Friedmann equation. This is it, 2 pi over 3g rho. And I forget about the special curvature, which may sometimes help. Then, if I differentiate this with respect to time, then I get 2h dot equals to 2 pi over 3 g rho dot, and rho dot, remember, is minus 3h rho plus p, right? For homogeneous and isotropic universe from the energy conservation, covariant energy conservation, you know that rho dot is this. Okay? So this tells us that h dot, this is a consequence of the Einstein equation, is minus 4 pi g times rho plus p. Okay? Now, if you have one of these scenarios, then the Hubble parameter increases in time. Indeed, if you have contraction, then it's negative, and then it becomes positive, so it has to increase in time to have a bounce. If you have genesis, the Hubble parameter is 0 initially, or very small, and then it becomes large. So again, it increases in time. Increasing in time means that you need to have, in both cases, p plus rho plus p negative, right? And this is a difficulty, because if you look at conventional field theories, then you don't have this inequality. You have the opposite inequality instead. And it was believed for a long time that this kind of inequality is not possible to have in healthy theories. This is called violation of null energy condition. Null energy condition is the weakest energy condition you can think of. There are various energy conditions in the in general relativity, and there are, singularity theorems proven by making use of, by assuming various energy conditions to hold. And this is the weakest energy condition one can think of. In general terms, it means it requires that the projection of energy momentum tensor onto any null vector means that it's light-like, so E square is equal to 0, that the projection of energy momentum tensor on any null vector is positive. This is called null energy condition. And this inequality here obviously violated, because in our setting we have only T naught naught, which is rho, and Tij, which is delta Ij times P. Right, let's see. So, is that correct? Minus. No. No, it's yeah, it's delta Ij times P, and therefore, if you choose your light-like vector in locally Lorentz frame as n mu equals to 1, 1, 0, 0, then what you get is precisely that if null energy condition is satisfied, then P plus rho must be positive. Okay. So this requirement that P plus rho is negative violates null energy condition. Okay. And it's more or less straightforward to convince oneself that the simple field theories you can think about actually satisfy null energy condition. Otherwise, they have problems. What sort of problems? One problem is that, in principle, that can emerge is the problem with ghost. And to illustrate this, there is a very simple way to violate the null energy condition, to have this relation P plus rho negative valid, if one introduces the wrong sign of kinetic term for the scalar field, d mu phi squared plus or minus, doesn't matter, v of phi, okay, minus. So suppose you do this, and here is the wrong sign in my choice of signature, plus, minus, minus, minus. This is the wrong sign of kinetic term. So and it immediately violates, for homogeneous field, it immediately violates null energy condition, because T00 is phi dot squared plus V, and Tij or P, you immediately calculate it from this Lagrangian, and you find that it's minus 1/2 of phi dot minus V. Okay? So that their sum, P plus rho, is just equal to minus phi dot squared, minus phi dot squared, and therefore it's negative. But obviously this is a pathological theory, because quanta of this field phi have negative energies. Once you have arbitrarily large negative energies, right? And this means that your vacuum is going to be unstable. You can create quanta of this sort, negative energy quanta, together with conventional photons, for example. So phi, so like this, phi, gamma, gamma. You have gravitons in between, not necessarily, since we are dealing with theory which involves gravity, and everybody interacts with gravity. So even if these guys don't interact with anything else, they interact with gravity, and this will not be allowed in conventional theory because of energy conservation. If these phi's had positive energies, then by energy conservation this would not be allowed. But once these guys phi have negative energy, ghosts have negative energy, then there's no problem to create them from vacuum together with photons. Okay, and if you are in the Lorentz preserving theory, then you don't allow that, because if you can create these pairs in one reference frame, then you can boost the whole process. It will also be allowed. So you create not only photons back to back, but also photons moving forward, and these guys moving forward as well, because they have not only energy but also momentum of the opposite sign. So you can boost the whole process, and it will still be allowed. So you have infinite phase space for this process. You have to, in other words, integrate over the Lorentz group, and the integral over Lorentz group is infinite. Lorentz group is non-compact. So you have, even though you have gravitational interactions only, once you are in Lorentz invariant theory, then you immediately have catastrophically unstable vacuum. So people have discussed the possibility that we have Lorentz violating theory, so then that this argument doesn't work, and these ghosts have possibly limited energies, and then the cutoff is on the order of a few MeV, because this process will create for you photon pairs from nothing, and cosmos will shine with photons, and there's no signal of this sort. So the Lorentz violation must happen for these guys, for these ghosts at MeV scale, which doesn't seem plausible. So ghosts are not allowed once you're talking about Lorentz invariant theory, which has Lorentz invariance up to the energy scale of larger than a few MeV. Okay? So ghosts are negative energy particles, negative energy excitations. Another possibility is what's called gradient instability. Gradient instability which occurs if I have this kind of theory. If my Lagrangian in some background has conventional kinetic term, but unconventional sign of gradient term, like this, d phi squared, plus possibly potential terms. Okay? Then if I write down, this is the wrong sign here now. Okay? So my equation will be like this, phi dot dot, plus Laplacian of phi, plus possibly phi squared term is 0, which means that my phi will go like e to the plus k. If my momentum is high, then I can forget about this mass term. If for high momentum, it will go like e plus chi t I k x, right? That will be solutions, plus or minus. This will be an exponential instability. Once you have small perturbations, then these perturbations will grow exponentially, and that's again no good. Okay? That's called gradient instability, and one can face this gradient instability. One has to worry about this gradient instability if you think of non-trivial backgrounds. Now, it's relatively simple to convince oneself that in conventional field theories you have either ghosts or gradient instability if you would like to have the null energy condition violation, in particular p plus rho in homogeneous background, negative. Okay, that's there is a simple argument by Dubovsky, Gregoire, Nicolis, and Ratazzi of 2006. Let me reproduce this. So suppose you have a Lagrangian which is a function, some function of xij, and in this business fields are often called pi. Pi I are just a collection of scalar fields, and xij are their derivatives, d mu pi I, d nu pi j. Okay? Then this is the conventional type of Lagrange, d mu, sorry. Conventional type of Lagrangians one can think of, which involve first derivatives, and then you calculate the energy momentum tensor and find that p plus rho for homogeneous field, if my pi depends on time only, and that's what I want in my cosmological context, then this p plus rho, well, you straightforwardly calculate the energy momentum tensor here, you get 2 df dx ij pi dot I, pi dot j. And this generalizes the formula I just erased, where my p plus rho was equal to phi dot squared. Okay, so to have null energy condition violation, you need that this Fij, f df dx ij, not positive definite matrix, right? You have to have negative eigenvalues of this symmetric matrix. On the other hand, if you write down perturbations about your homogeneous solution, so you write down the quadratic Lagrangian for perturbations, you write down that pi is classical pi, for which this this relation holds. So I have classical pi plus delta pi, and delta pi are perturbations about the solution, whatever it is. The solution itself is homogeneous, delta pi is not, and then you get some, term which involves derivatives, pi I, with respect to time. Doesn't matter what they are. And also, then, importantly, what you have is minus df over dx ij times di delta pi I di delta pi j. Okay? Again, it's straightforward. You just take this expression here, insert into this Lagrangian, expand up to quadratic, delta, up to quadratic order in delta pi, and you get this expression here. Now, the point is that once this thing is not positive definite, your gradient term is not positive definite, right? Here. You have a negative eigenvalue. And then you're back to either ghost or gradient instability. Because if this mode, which has positive term in this in here in this Lagrangian, positive special gradient term in the Lagrangian, mode either have negative kinetic term, then it's ghost, or it has positive kinetic term, but then it's gradient instability. The sign here is wrong. Okay, so this tells us that conventional theories involving first derivatives only do not allow healthy backgrounds which do not have either gradient or ghost instability, or both. Okay? Well, there is a loophole here which goes under the name of ghost condensate. And the loophole here is that this matrix may be non-positive definite, but only slightly. Okay, so you're close to a situation when this matrix has actually a zero among eigenvalues. Okay, so basically this means that the null energy condition is violated, but only weakly, very slightly for some reason. You are very close to the situation when p plus rho is equal to 0, but it's slightly negative. If it is just slightly negative, this term is wrong. It has wrong kinetic term. It has wrong gradient term. But this is very small. This could be very small. And then you have to think of adding first gravitational interactions, and also you think of adding higher order terms. You treat them normally as irrelevant operators, right? Or in other words, you forget about them in the low energy effective theory. But here, since I'm nearly at 0, this term may become important. Okay, the higher order terms may become important and save the day. That's the idea behind the ghost condensate. However, it turns out that it's not in fact strictly necessary to use this loophole to start constructing these genesis or bouncing universe scenarios. One can think of a different possibility, and this is interesting. It's called, nowadays it's called Galileons, or generalized Galileons. But in fact, this kind of theories is known for a very long time. Have been written, well, it wasn't known, it was written very long time ago, but it wasn't known for a long time. I mean, okay, this goes under the name of Galileons. And in fact, it was introduced by Horndeski in 74. Horndeski. It's in 74, and went unnoticed for a long time. Then it was rediscovered by Horndeski. Rediscovered by Faley, Govatz, and Morozov in completely different context in 91, and then again rediscovered by Nicolis, Ratazzi, and Trincherini. In 2009. So that's, you know, these papers were not quite appreciated, and only, you know, in retrospect, it turns out to be, they turned out to be completely irrelevant here. The simplest example of this, the idea is to have theories whose Lagrangian contain higher order terms, not only first order derivatives, but higher order derivatives. Normally, if you have higher order derivatives in the Lagrangian, then your field equations become also higher order, not second order, but fourth order, typically. And with fourth order equations, you again have problems with ghosts or gradient instabilities. Now, the point here is that you can have still, even though you start off with Lagrangian, which is higher order in derivatives, you can still have second order equations, amazingly. So the simplest Lagrangian of this sort is like this. You have some function f of x and pi for just one field, plus, let me call it k0, plus k1 of x and pi, and box pi. Okay, where x is d pi squared. So the first term is conventional, has only first derivatives in it. The second term has second derivatives. The box is di, di, d mu, d mu. Okay, it has two derivatives in it, but if you just do the algebra and figure out what the equations of motion are, you will see, to your surprise, that these equations of motion are actually second order. I invite you to do this simple calculation. You will figure out that higher order terms in this equation, in general, there are third order terms, and these third order terms cancel out. That's the simplest version of the Horndeski theory, or Galilean theory. You can actually generalize this, and there are a few more terms you can add, and the overall structure is like this. Your Lagrangian is nth Lagrangian is some function kn of this x and pi, field that and its first derivatives, and then there is a peculiar structure like this: mu1 d mu n, and it is anti-symmetrized with respect to all these lower indices acting on pi. Okay, Because of this peculiar structure, you again can check that the equations you are going to obtain are second-order differential equations, rather than, in principle, you would think that these are nth order, n+1 order differential equations. Okay? N is arbitrary, yes. Sorry. Should have written different. D mu 1, d mu n. That's, yeah, I should have written this way. Yeah, sorry. Yes. Okay, so these are 2n derivative term. Okay, you would expect that the equations of motion are 2n+1 derivatives, involve 2n+1 derivative terms, but they don't. They all the high derivative terms cancel out because of this antisymmetric structure. Okay. So for d equal 4 in 4 dimensions, you have 4 terms of this sort. N can be 0, 1, 2, 3, and 4. N is less than or equal to 4, otherwise you would not be able to make antisymmetric combination. So there are 5 Lagrangians, 1 standard, and 4 high derivative Lagrangians, which in the end lead to the second order differential equations. And with this you have more freedom, right? You don't have so strong relationship between the sign of your gradient or kinetic term and the expression for energy momentum tensor. Okay? Yeah? What? Why is it not? Yeah, because let's write down the second term. d nu sorry, what I'm writing? Yeah, I should have written pi here as well. Sorry, yeah, okay. I apologize. Sorry, it's second order terms everywhere. Okay. Yeah, okay. Right, okay. These are second order Lagrangians. What I was talking about, okay. Right, anyway, you have more freedom, and in particular, you can do a very simple example. Let's do a simple example. So let's take the Lagrangian. I will use this later on as some function of y. This will be a subclass of the Lagrangians I have written before, which has dilatational symmetry, which makes life a lot easier. 2 pi box pi, where y is e to the minus 2 pi d pi squared. Okay. So this is subclass of the Lagrangians of the first kind, which has dilatational invariance in them, so that pi goes to pi of lambda x plus logarithm lambda is a symmetry of this Lagrangian. Why is that? That's my choice. Just to illustrate what that you can still do. You are able to indeed to have healthy theory which violates null energy condition. Okay, so let us work in Minkowski space. Okay, and because of this nice symmetry, it's straightforward to find a solution e to the pi c of t homogeneous solution to the field equations, which is like this: 1 over square root of y star minus t, okay? Where t goes from minus infinity to 0, essentially. 0 is singularity, but otherwise it's a nice solution. So for this solution, you can check that this expression here is a constant. Y is y star. So everything boils down to the algebraic equation, which involves, let me not write it, it's not particularly eliminating. This will become algebraic equation like minus f plus 2y star f prime. Okay, let me write it. Minus 2y star k plus 2y star squared k prime equals 0. This will become algebraic equation. This f and k are evaluated at y star, and it's their derivatives as well. So it's an algebraic. It becomes an algebraic equation for your parameter of your solution, y star. Okay, and you know, you have functional freedom in your theory, so you can think of various forms of these functions, and that gives you the solution. Now, the point is that for this solution, the energy density is 0, and that's obvious because at minus infinity you have your field pi e to the pi going to 0, which means that you are in the essentially static background. So energy density is 0. Pressure, ij component of energy momentum tensor is e to the 4 pi classical times some combination of the same functions, f minus y star times k. Okay. So again, you have functional freedom, and you can have solution to this equation for which this pressure is negative. Okay. And importantly, you have this term here, which is this non-trivial part containing second derivative term box pi. So this is the reason why you can have negative pressure and at the same time positive value of f, which turns out to be necessary here for okay, and then you can calculate the quadratic Lagrangian for perturbations, and let me call this z of y, and the solution is z of y star is 0. That's the classical solution. And then it's again straightforward to calculate the I'm not doing these calculations, it's just a simple thing. You can calculate the quadratic Lagrangian for perturbations. You are worried about the ghosts of gradients instabilities. Yeah. Why is this? It's by my definition minus 2 pi d pi squared. It's a function of it's a definition of this y. Okay, and it turns out that on this solution, this combination here is just a constant, this particular constant here. Okay, right? This combination of your field, if you plug in this expression in here, will give you y star. Okay, so y is okay, the definition of the variable. All right. Anyway. So my Lagrangian for perturbations will have this form, e to the pi c z prime where z is precisely the same combination here, evaluated at y, and okay, delta pi dot squared minus e to the 2 pi classical, another combination, let me call it v, di delta pi squared, the gradient term, and there is also a term proportional delta pi squared. Now the whole point here is that this v is yet another combination, which is f prime minus 2k plus 4y star k prime on the solution. Okay? So what we get is, you know, we have functional freedom here everywhere. Right? Did I write it correctly? Yeah. Anyway, the point here is that this is the requirement for the solution. My coefficient in here involves different combination of functions. Pressure, yet another combination of functions. And this guy involves second derivative. So you can play with functional form of your functions and make sure that everything is fine. Everything is fine, meaning that even the not only v is positive, but also the coefficient of pi dot squared is greater than v, which means, first of all, that it's positive, there's no ghost, and also that you're subluminal, that the perturbations here are subluminal. And the simplest example of this sort is that you can have linear and quadratic functions, f modular overall constant minus y plus 1 plus alpha over 2 lambda cube y squared, and k equal to 1 over lambda cube y. This simple choice will produce healthy background in the sense that there is a solution to this equation here, and all these inequalities are satisfied about this background, provided that this alpha is in some range from 0 to 3. So so you can convince yourself that you do, the bottom line is that there is a functional choice of your Lagrangians such that you do violate null energy condition, and yet the background is healthy. It has no ghosts, no gradient instabilities, and if you worry about superluminality, then it's subluminal. The perturbations go subliminally. That's why these Galilean theories are interesting. They get around the problem with null energy condition. Okay. Any questions so far? Right. Now, using this, these guys, Nicolis, Ratazzi, and Trincarini, were able to produce genesis scenario, and with the same Lagrangian I wrote, with the same solution I wrote, I did that in Minkowski space, but if we, let's see what happens if we are working in general relativity. So we have this solution here. We have negative pressure, which goes like, in this case, minus some scale, whatever you have in your theory, divided by y star squared t star minus t to the fourth. That's no matter what precisely the functions you have on the solution, this pressure in the absence of gravity is this. Okay, that's its functional behavior as function of time. Sorry, minus t. That means I have set t star equals 0. Okay? So, does it produce the non-trivial gravitational gravity? Yes, because I have erased this, but we have h dot equal to minus 4 pi over m Planck squared, which is g, Newton's constant, p plus rho. My rho is 0, p is to the leading order given by this equation here, and therefore your h, the Hubble parameter, can be found by integrating this relation, and you get h is 4 pi over 3 m to the fourth m Planck squared. This is m Planck squared y star, sorry, squared, and t star minus t cube. So obviously once you have negative pressure, you start generating the Hubble parameter. That's its expression. At early times when t is large and negative, the Hubble parameter is small and it increases. Okay, and you find how it increases. It increases like 1 or minus t cubed. Okay, so for some time it's small. It doesn't affect the evolution of this classical field. So what I'm doing here is perturbation theory in 1 over m Planck squared. And clearly, this tells you that energy density is also non-zero to the next order, and it's proportional to m Planck squared h squared from the Friedmann equation, and therefore is proportional to 1 over m Planck squared, m to the fourth, m Planck squared minus t to the sixth. Okay, m to the eighth. Okay, so the energy density remains small in the beginning. So you do have the situation, you do realize the situation when initially at large negative times your space is Minkowskian, Hubble parameter is negligibly small, energy density is negligibly small, but since there is a non-trivial background with negative pressure, everything builds up. The Hubble parameter increases as time becomes less and less negative. Energy density increases, so you speed up your expansion of the universe. Okay, that's basically genesis, right? You then have, of course, to make sure that this stage ends up, right? It has to terminate at the energy density, which is at this time sitting in the Galilean field, should get reprocessed into heat. That's, I think, rather non-trivial and not quite worked out aspect of this scenario. And unlike inflation, which is, 25 years old, this is only 5 years old. So there is a lot of room to work here. For example, and in particular to work out plausible scenarios of how the energy stored in this Galilean field can be transferred to heat. Right, so we got around this problem with null energy condition, and we have seen that you can in principle have the genesis behavior. Now there is another problem. If you think of the first scenario with contraction as an initial stage, it doesn't apply to genesis, it applies to scenario with contraction and bounce. And this is again known for a very, very long time, but it shows up in this context quite remarkably. That has to do with Belinsky-Lifshitz-Halatnikov phenomenon. To illustrate it, okay, let's consider the contracting universe. Okay, so we're talking about contraction. And let's consider gravitational waves, gravitons, in this universe. Remember, we had this equation for gravitons, which I write in cosmic time, 3h dot plus k over a squared h equals 0. For each of the polarizations, we have this equation for gravity waves for tensor perturbations. And that's equivalent to what I have written in terms of conformal time. For now, it's more convenient to work in cosmic time. Okay? So, remember this h, first of all, it's negative. We are at contracting stage. And second, it increases as in modulus as time goes on, right? We're contracting. So this term, which was friction term, becomes now antifriction. Okay? And that's dangerous because antifriction, you know, tends to destabilize your system, right? So in this case, we have the opposite situation to expanding universe, obviously. Yeah, one second. The expanding universe, my physical momentum at early times when h is small, and the physical momentum was larger than the Hubble parameter for, you know, say radiation domination or matter domination or something like that. This we start off with subhorizon modes, and this subhorizon mode eventually enters the horizon. That's what we need, and that's what happens here. Yeah. In instabilities, not that I know of. Are there, Enrico? No, I mean, if you would. No, with judicial choice of these functions, you can have it stable and subluminal. Right, okay, let's come to this issue. This is a different issue. This is an issue with contracting universe. With contracting universe, you have Hubble antifriction. So let's see how the solutions behave in the subhorizon regime, late time regime, when t is small, and suppose that my h is some constant over t, right, which is typical for, say, radiation or matter domination, or for other generic equation of state, you get this behavior. Just take it as an example. Then we've got that this equation here in the superhorizon regime is simply h dot dot plus 3h. Yeah, it's negative. T is less than 0. Plus 3h h dot equals 0. Now my Hubble parameter is negative. I have two solutions. H dot is either 0, which was our constant mode, right? We had it. And the second solution is kind of dangerous. It's T to 3 alpha. Okay? Which means that the metric perturbation is either constant in time, that's our constant mode, or it goes like 1 over modulus T to 3 alpha minus 1. Okay? So, the second solution for if alpha is not too small, it will blow up. The system becomes unstable because of the Hubble antifriction, and instead of having it's snowing there. Amazing. Instead of being homogeneous and isotropic, you are going to get inhomogeneity and anisotropy because of these perturbations growing, right? So you better require, otherwise your universe will become random, you better require that alpha is less than 1/3, okay? Otherwise you have very inhomogeneous and anisotropic universe towards the end of contraction, right? And that's not what you want. You want to have a universe which starts up its expanding and hot stage being already quite homogeneous and isotropic. And here you ruined homogeneity and isotropy, so you would like to have this alpha less than 1/3. Alpha less than 1/3, yes? Well, because this, as t goes to 0, we start off from minus infinity and t goes to 0. As t goes to 0, this thing here, if alpha is greater than 1/3, blows up. And remember, this is amplitude of gravitational wave. So we have metric perturbations which blow up as time goes to 0. So we have very inhomogeneous and anisotropic universe. And that's not what we want. We want our universe to remain homogeneous and isotropic, and even more so if we start off with inhomogeneous and anisotropic universe, we want it to become more homogeneous and isotropic towards the end of contraction. Right? That's the opposite case. So we would like to have alpha less than 1/3. Alpha less than 1/3, yeah. Vector perturbation. Well, then no, I don't think so. With if alpha is less than 1/3, then vector perturbations don't grow as well. In both tensor and vector perturbations are safe. I think. I have to check that, but my understanding that all perturbations tend to a constant as time goes to 0. Anyway, what does this mean? This means that we know that the h is alpha over t, as we wrote here, which means that a goes like t to alpha, right? Rho goes like h squared, and it goes like 1 over t squared, right? So what I'm aiming at is that we know that rho dot is minus 3 a dot over a, or h 3h rho plus p. I'm trying to figure out what is the equation of state. Okay, I use this, I plug this 1 over t squared in here, and I get rho dot is yeah. So let me write down that this thing here is 1 over scale factor to 2 over alpha, right? Since my a is t to power alpha, then rho goes like this, and if I differentiate it, I'm going to get minus 2 over alpha a dot over a rho equals to minus 3 a dot over a rho plus p. Okay, and from that I figure out the relationship between pressure and energy density. I get that p plus rho over rho is 2 over 3 alpha, right? Which means that p over rho is 2 over 3 alpha minus 1. So if I want my alpha parameter, my parameter that determines the Hubble function, Hubble h, to be less than 1/3, this means that p over rho must be greater than 1. So we can avoid this Belinsky-Lifshitz-Khalatnikov problem, which I phrased as a growth of perturbations towards the end of rolling stage. You can avoid this if your equation of state is such that p is greater than rho. Right? Weird. For radiation domination, p is 1/3 of rho. For matter domination, p is 0. And we need what's called stiff equation of state. Pressure greater than energy density. Then you smooth out your perturbations. Your perturbations will tend to a constant, whatever they were. They do not grow within the, outside the horizon. Everything is fine, but you need this strange equation of state. So if you want to construct the bouncing universe, then you want the matter at the bouncing at the contracting epoch to have stiff equation of state. And nowadays, again, this goes under the name of generalized ekpyrosis. Right? Contraction with stiff equation of state. You can, I mean, was discussed recently, relatively recently, in the context of ekpyrosis scenario. So you can think, you can dub it as generalized ekpyrosis. All right, I think I will skip the other version of the original version of Belinsky-Lifshitz-Khalatnikov treatment. Now the question is, can you actually have matter that has stiff equation of state? The answer is yes, even though, again, you have to have some exotics, right? Exotics meaning something that is not impossible, but not seen in nature. Well, there are many things that haven't been seen in nature, including inflatons, so why not this? Now, so we want to have p greater than rho, and let's try to do this in conventional field theory, scalar field theory. We know that for standard field theory with a certain potential, rho is again phi dot squared plus v, where v is the scalar potential, and p is a half phi dot squared minus v. Okay? So P is greater than rho means that potential must be negative. So you, instead of, inflationary case when the potential is positive, you want to roll down the potential, but this potential is negative. Right? It's like this. This is V, this is phi. So if you roll down this potential here, then you do have stiff equation of state. And in periodic scenarios, people were talking about the exponential potential, this part as an exponential potential, but that doesn't really matter. Once you have negative potential, you roll down negative potential, then your equation of state is necessarily stiff. Okay, so to construct this this model with contraction, bounce, and expansion, you can think of marrying this kind of scalar field with Galileon, which makes Hubble parameter to increase. And that will be an example, and there are examples of this sort constructed. This will be an example of healthy bouncing cosmology, which doesn't have any instabilities or Belinsky-Lifshitz-Khalatnikov problems, and yet it's an example, proof by example. So the bottom line here is, if you want to construct a bouncing universe scenario, you can do this, but for that you need to work a little bit. You have to invoke negative potentials at contraction epoch. You have to invoke Galilean fields in the bouncing epoch, and that will give you an example of smooth bounce without any instabilities like ghosts or gradient instabilities in between. Okay? Probably will not go into more detail here, but now there is a question. After all, what we are about is to produce density perturbations, right? Why we think there must be some epoch before the hot epoch. Well, we want to produce density perturbations. Can you do that? Yes, you can. Again, you have to work. You have to, it's not immediate that you do that, but still you can. And let me give you an example of one approach which I'm involved in. And the idea is, now one can think of inflationary scenario. Why does inflationary scenario produce for you flat spectrum, flat power spectrum? One can think of flat power spectrum as a scale invariant spectrum, right? We have seen that power spectrum doesn't have intrinsic scale in it. Okay, it's decay of k. So you can trace it back in the inflationary context to the fact that let me come for a second to this to de Sitter inflationary like behavior. In the de Sitter case, you have this metric here, and as I mentioned, this metric has quite some large symmetry, which is a symmetry under SO 4,1. In particular, it involves dilatations, right? You can make a dilatation of the coordinate x and at the same time shift time so that the metric becomes remains invariant. Okay? Now, since I don't want inflation, I don't want this symmetry, but I can actually play with larger symmetry, which is conformal symmetry, SO 4,2. Okay? And conformal symmetry also involves dilatations, and therefore you might think of using conformal symmetry as a symmetry behind the flatness of the power spectrum. Okay? Realization is quite simple. I think I will not go into any detail, but the realization is quite simple. And in fact, let me give you a very simple example with Genesis. Okay? So, as we saw, our e to the pi classical was a solution like this, y star minus t. Okay? It actually resembles very much the Hubble parameter at inflation. The scale factor at inflation. In the conformal coordinates, the scale factor at inflation, A of eta, goes precisely like minus 1 over h eta, if h is a constant, right? So there is a similarity here. And it's not accidental similarity, because if you have your Galilean theory conformally invariant, then this background breaks conformal invariance down to the theta, SO4, 1. Okay? And then you can use remaining symmetry to make flat power spectrum. As an example, let's consider another scalar field. That's the original version of Trincarini and company. Let's introduce an extra field, call it theta, which is scale invariant under scale. Which is invariant under scale transformation. And let's require that the Lagrangian for this theta is scale invariant. Action is scale invariant. We are still in Minkowski space, remember. We are doing everything in Minkowski space, assuming that, say, in the contracting scenario, we are at very early stage when the universe was nearly empty and the Hubble parameter was nearly 0. So we are essentially doing Minkowski space. Then the Lagrangian for perturbations, let me write the action for perturbations rather, is d4x d theta squared, and under the scale transformations, p goes to p plus constant. It shifts under scale transformations. Okay. If I scale, for example, in this, if I scale time by a factor, then this will lead to a shift of the classical field. In the Lagrangian I wrote before, which involved these arbitrary functions, is still the case. You have scale invariance, and scale invariance involves the shift of the pi field, right? I wrote it before. Pi goes to pi of lambda x plus logarithm lambda. Okay. So if you want this action to be scale invariant, you just multiply it by 2 pi. Okay? So if you insist on scale invariance, if you don't introduce potential terms for this new field, think that this trivially transforms on the scale transformation, that's the scale invariant Lagrangian you write. Now, if you have this background, lo and behold, what you're going to get is dt d3x in the background. In this classical background, you will get y star squared t squared d theta squared, right? And that's precisely the same Lagrangian that you have for massless scalar field in the Sitter space, because there, in conformal coordinates, my action was integral d eta dx a squared d whatever theta squared for any massless scalar field, modulo 1/2. Yeah, that's what I get for massless scalar field in conformal time, in conformal coordinate x. And if I have the de Sitter behavior, then it's exactly the same as here. So there is a equivalence or similarity, if you like. If you have a field that lives in this background, that its effective metric is essentially de Sitter metric. What it feels is de Sitter metric. Even though the real metric in spacetime is Minkowskian, since my field interacts with a non-trivial background, the effective geometry for this field is de Sitter geometry. That's another manifestation of breaking. If you have conformal theory for this Galileon, then you break conformal symmetry down to de Sitter symmetry. That's another manifestation of this fact. Okay. So then immediately, I mean, you don't have to do any work, because you know that the scalar field in the de Sitter background that we calculated becomes superhorizon at late times. Here, it will become superhorizon at late times as well, but the horizon refers to the effective metric here, the metric that this theta field fields. So the field freezes out, just like here. The field freezes out, and it develops flat power spectrum. You don't need to work. You know the answer. It's the same story as for massless scalar field in de Sitter space. So theta, in the end, has perturbations that have constant k-independent power spectrum, flat power spectrum. And that's, to the zeroth approximation, what you need, right? So okay. And there are various reincarnations of this scenario. Basically, the whole point, which was studied in much detail by Hinterbichler and Khoury, and also by Kreminelli, Joyce, Khoury, and Simonovich recently, is that this pattern of symmetry breaking actually determines a lot for you. The conformal symmetry is so large, and this pattern is so unique, that you gain a lot of information just from the fact that you break by this rolling, assuming the homogeneous background that breaks this symmetry in this fashion, breaks conformal symmetry down to de Sitter. You gain a lot of information without even having particular form of the action. Okay. Right, now, so far so good. What we were able to get is a flat power spectrum of field perturbations. Again, we know that there are possibilities to convert field perturbations into density perturbations, right? That we discussed yesterday when we studied curvaton mechanism. That's precisely what it does, right? You have power spectrum, nearly flat power spectrum of a certain field, curvaton in that case, and we were able to reprocess its perturbations into density perturbations, adiabatic perturbations. And obviously you can use the same idea here, right? So you can reprocess perturbations in your field theta to density perturbations at some late stage, say at radiation domination stage. So far so good. Now the question is, can you in fact discriminate? What's special about this kind of scenario? Can you figure out any difference between say the curvature scenario of inflationary universe? Well, first of all, you don't, since there is no inflation, since there is no exponentially growing scale factor, gravity is mild. I don't need strong gravity at all. Or if I have strong gravity, it's completely different from inflating universe. Strong meaning fast contraction in this case, or anyhow, there is no reason for you to expect that you generate gravitational waves, tensor perturbations. So one discriminator is tensor modes, right? Especially, I think it would not be possible in this kind of scenarios to obtain flat power spectrum of gravitational waves. In concrete cases, you get very blue power spectrum of gravitational waves, which make them essentially unobservable. So one discriminator between inflation and everything else is tensor modes. Okay, so that's way to falsify all this set of ideas, right? If gravity waves, tensor modes are observed, forget about all these developments. Okay, so it will be very, very interesting indeed to see effects of gravity waves. In the particular conformal scenario, there is another phenomenon which I would like to illustrate explicitly by using completely different model. By using completely different model. Let me be quick on it. So completely different model is this one. You start off with the phi to the 4 theory with wrong potential. D mu phi squared, I take it complex, plus lambda phi to the 4th. Okay, let's consider it at semi-classical level. So if I forget loops, then this is conformally invariant theory. Okay, in 4 dimensions. Right. So my potential here is negative, minus lambda phi to the 4th. That's the one of the possibilities for contracting universe, the stiff equation of state, a periodic type potential. But for me, that's not very relevant. Of course, I have to assume that this potential changes its behavior at very large fields. But let's consider the region of where the potential can be written in this fashion. Then you immediately find that there is a solution which is the same story, minus t. Let me write down here the end of rolling as a free parameter, t star. Okay? So t is my time, goes from minus infinity, and at t star you get, your field rolls down to infinity. Okay? So the same story, similar to Galileons. Now, if you look at the perturbations of phase of this field, that's why I took it complex, they will automatically, so this is the classical part, the Lagrangians for the phase will be the square of this classical part. I took it real for, without loss of generality, since I have U1 symmetry here. So this will be this modulus times d theta squared. So it's 1 over lambda t star minus t squared d theta squared. Precisely the same story. Precisely the same story as before. You get the same Lagrangian with effective metric, which is the theta metric. Okay. So you generate flat perturbations for theta, but that's not the main point. The main point is that you can now look at the equation for the radial perturbation. This is phase, okay? But in general, my phi is phi c times e to the I theta plus delta phi, where delta phi is real, okay? So I can look at the perturbations of these guys, of this part, and I invite you to work it out, but in this background, equations for these perturbations will be quite different from everything we know of. Perturbations for this delta phi will be like this: delta phi dot dot plus k squared delta phi, which is obviously coming from gradient, and then there will be minus 6, which is unusual thing, t star minus t squared delta phi, with minus sign here. And that's different from what we have in the case of inflationary universe, or in the case of the phase, which we had here. But the fact is that this 6 makes solutions quite different. And in particular, if you start off, if you look at, again, at large negative times, this term here is irrelevant. You have simple oscillations, right? So you can write initial condition as e to the minus I kt, okay, as t goes to minus infinity, times a k, where a is the creation operator, 1 over square root of k, the same story as we did before, but in the subhorizon, effective subhorizon regime, when tk is less than 1, you end up at something different. In the inflationary case, it was flat power spectrum, meaning that the dependence was 1 over k to 3/2 power. But here, you've got 1 over k to 5/2 times t star minus t squared, okay, times the same a of k plus Hermitian conjugate. And that will give you power spectrum which is red, p delta phi 1 over k squared, okay? And that's, again, is a consequence, in fact, of this symmetry breaking. It repeats over and over again in whatever models you have for that employ conformal symmetry. So you have unusual situation. That doesn't happen in inflation, at least in simple inflationary models. You have perturbations which are not directly relevant to the density perturbations, but there are perturbations of your field, of some of the fields, in this particular case, the radial real part of the field, which have red power spectrum. And that's not an innocent thing. It can be used to discriminate at the nonlinear level this kind of models from simple inflationary scenarios. For example, the non-Gaussianity that you produce when your field theta interacts with this red, with these red perturbations, this non-Gaussianity has a particular shape which is not present typically in the inflationary models. So there are possibilities to discriminate, and they are based on the fact that there are peculiarities of the conformal mechanisms related to the pattern of symmetry breaking. So that was to illustrate that alternatives to inflation still have a right to exist. They are contrived. They are not very simple. They are not as simple as inflationary, single-field inflationary models. But now, with data from Planck, single-field inflationary models are also not very, I mean, you have to work to make to meet ends. So there is the alternatives to inflation have right to exist. You can design models that are consistent, that are not plugged by instabilities, and also you can design mechanisms. This is not the only one, of course, which produce for you flat or nearly flat spectrum of density perturbations. So from the observational viewpoint, for the moment, they are indistinguishable. This brings me to overall conclusions. Overall conclusions is that first of all, we have to appreciate that we may be confident today that the hot cosmological epoch was not the first epoch in the universe, in the evolution of the universe. Now, what was the epoch that preceded that one is still, you can debate, is still a question. That was the epoch of generation of cosmological perturbations. The best guess is inflation, of course. But inflation is not a theorem. That's one message of this lecture. Inflation is not a theorem. You can design alternatives. They are as consistent with data as inflation is, although they are designed a posteriori, we should admit. Right? It's not that inflation was designed before the wealth of observational data started to confirm it. These ones have been designed a posteriori. So, I mean, the status is different, but that's maybe a sociological thing. It's not necessarily scientific. And the bottom line is that we need to know more about perturbations. We know only very, very basic things about perturbations. We know they're Gaussian. We know they have almost flat spectrum with a little bit of tilt, but you know, if you have a symmetry that, like conformal symmetry that gives rise to the flat spectrum, you break your symmetry slightly, explicitly, and then you get tilted spectrum, no big deal. So we know there is a tilt, we know they're Gaussian. We haven't seen tensor perturbations yet, so we have very limited, grossly speaking, we have very limited knowledge of the primordial perturbations. So we need more tensors, non-Gaussianities, statistical anisotropy. If any of these will be found, we will be a lot more confident on what was happening in the early universe before the hot epoch. For the time being, there are options, and there are things to work out. There are many things which are not understood. Thank you.